It's really great to be in beautiful Buenos Aires. I remember we actually started talking about Hyperbridge at the first Subzero in Brussels. I've been discussing a lot in our talks about the cryptographic mechanisms that make Hyperbridge possible. And I realized that I've actually not discussed the cryptoeconomic mechanisms that will keep Hyperbridge sustainable and powered by a decentralized network of agents, sustaining the network even after Polytope Labs and the developers of Hyperbridge are no more. And so, yeah, let's get into it, actually. So the Hyperbridge protocol is actually not one thing. It's not the Hyperbridge parachain. It's not the relayers. It's not Polkadot. It's actually this combination, this amalgamation of every single thing. So we have the consensus relayers, we have the messaging relayers, we have the block producers, the collators on the network, and we also have the Polkadot protocol. And Hyperbridge cannot function if a single member of this set is not present. If Polkadot is not available, then you no longer have the Hyperbridge protocol. If any of the relayers are offline, then the protocol is not going to function. So we need incentives and we need cryptoeconomic guarantees that bring all these participants together to facilitate the protocol, right? So a very, very high-level overview of how I like to think about Hyperbridge, especially if you're familiar with the OSI model, you know, especially for TCP, you have your infrastructure layer, the physical link, you have the application layer, you have the presentation layer. And so we've actually sort of replicated this model for cross-chain interoperability. So at the top is actually Polkadot. Polkadot is actually what enables the rest of the Hyperbridge stack. And then we get, of course, to the Hyperbridge network itself with the parachain network. And then we have the relayers at the bottom who are basically the physical link of the Hyperbridge protocol, right? And so, you know, they're basically connected to all the external networks. And they're going to collect some information. They're going to collect proofs. They're going to collect data. And they're going to feed that into Hyperbridge. Hyperbridge is going to do some verification. And after that's done, then Polkadot is going to prove what Hyperbridge has done, right? It's going to say, OK, all of this work is correct, and it looks good to me. So you can see the Hyperbridge network and the relayers are untrusted. There are no cryptoeconomic guarantees at this layer. But once the work moves up to the top, where Polkadot exists, which is the trusted layer, then we start to have some cryptoeconomic guarantees, right? So here's how I like to think about it, right? Like, so the Polkadot network is watching both Hyperbridge and both the relayers and ensuring that they're both doing the correct thing. The relayers, they basically work with the collators, right? Because they collect transactions and they submit to the block producers to include these transactions in the block. And the collators are obviously watching the relayers because they're checking that the relayers are submitting the correct transactions. And so, basically the roles of everyone on the network, the relayers, they're going to collect and submit transactions to Hyperbridge. These transactions contain proofs of consensus, proofs of transactions, cross-chain transactions that need to be exchanged. The collators, well, they're just going to verify these transactions, right? They're going to verify that these proofs are correct. And if they are, they're going to put them in a block. But if they're not correct, invalid transactions do not make it into a block. And this is very critical so we can save up critical block space. And once Polkadot, once the collators are done, they're going to put all these blocks and submit them to Polkadot. And Polkadot is going to verify these blocks because that's actually what it does, compared to your other roll-up platforms that actually require you to prove your blocks. Polkadot actually proves your blocks for you, right? So if you remember Ethereum, you have to generate a ZK proof of your L2 blocks, but for Polkadot does that job for you, right? And after Polkadot verifies your block, it's going to be like, OK, that looks good to me. It's going to generate a certificate or a receipt that your blocks are valid, right? And this is very important, and I'm going to get into this later on. So let's quickly look at the first agent on the Hyperbridge network, the collators, right? They're basically collect and verify interoperability proofs. There are two kinds of transactions that they expect. They expect consensus messages, and they expect cross-chain messages, right? And these things both have proofs. And they're actually not staked participants. Typically, you see blockchain networks require you to stake so you can be a part of the active set. we've taken a completely different approach to this. Rather than requiring some stake, we require a small bond in, of course, the bridge token, just so you can be eligible to be a collator. But in order to be selected as a collator, you actually have to burn reputation points. And these reputation points come from being an active relayer. So only relayers can become collators. You know, there's nothing else. You cannot bribe anyone to become part of the collator set. You do some work as a relayer, you put a small bond up to be eligible to be selected as a collator, and then with your points, the relayers that have the most points make it into the collator set. And this collator set is rotated every 24 hours. So every 24 hours, new relayers are eligible to become collators. And collators, well, they're paid for their work. They earn around 0.7 bridge for every block that they produce. And so if you miss a block, well, you miss the reward for that block. Moving on to consensus relayers. So consensus basically forms the foundation of cross-chain messaging, right? We need to see that the cross-chain transactions have been finalized. And for that, we need consensus proofs. But the problem is blockchains are constantly producing blocks, especially modern slot-based blockchains, right? Even if there's no transactions, they keep producing blocks, which means that Hyperbridge has to stay up to date with these blocks in order to verify new cross-chain transactions. And so consensus relayers are just basically constantly submitting consensus messages of these blocks, even if there's no transactions, right? Simply keeping the Hyperbridge blockchain up to date. And so they don't also pay any transaction fees to do this. Consensus relayers are in fact paid by the Hyperbridge protocol, right? They are incentivized by the Hyperbridge protocol to submit these transactions. They're paid in bridge tokens to do this. And so consensus relayers are constantly earning bridge tokens. And we'll move on to the messaging relayers as well. So, you know, just a very high-level overview. You have some external blockchain that's producing blocks. You have consensus relayers who sit in the middle of this blockchain and Hyperbridge. And what's going to happen is it's going to collect all these proofs of newly finalized blocks. It's going to submit these proofs to Hyperbridge, and the Hyperbridge protocol is going to give them some bridge tokens as incentive. So this keeps, ensures that consensus relayers are always online and are always ensuring that new messages are able to be exchanged with all the different blockchains. And so we have messaging relayers, and they're also, you know, very similar in function to consensus relayers, but they specialize in submitting cross-chain transactions. So when Hyperbridge learns of newly finalized blocks, the relayers are actually going to look at the previously finalized block, and they're going to scan in between these blocks and see if there's any new cross-chain messages that can be submitted to Hyperbridge. And once they see that, well, they're going to submit these messages and their proofs to the Hyperbridge blockchain, right? And the difference here, though, is that messaging relayers are not going to be paid all the time for this. In fact, it's the case that they have to pay Hyperbridge to submit these messages. Users, applications, they're going to dispatch cross-chain messages from any blockchain. They're going to put stablecoins, attach some stablecoins to these messages. Messaging relayers, they're going to see this message, they're going to bring them to Hyperbridge, and then Hyperbridge will allow them to withdraw these stablecoins. And they may have to pay the Hyperbridge blockchain if some target of message processed has been exceeded. But if not, the Hyperbridge blockchain is actually going to incentivize them. It's going to pay them in bridge tokens for this job. And this is just to incentivize people to keep their messaging relayers online so that, you know, anytime there's new messages, there's always someone to relay these messages. So similarly, with the consensus relay, you have some external blockchain. You have the messaging relayers that sit between this blockchain and Hyperbridge. And essentially, they just collect messages and they submit them to Hyperbridge. And Hyperbridge will either pay them in bridge tokens if the target for message process has not been met, or they have to pay Hyperbridge in the bridge tokens, just so Hyperbridge can also start to accumulate some tokens for revenue. And so we briefly see the requirements for running these relayers and running these collators. Relay software is very lightweight. All it does is it makes RPC queries to blockchain nodes. And so you don't really need a lot of compute or RAM for this. You can get away with like a 4-core CPU. You can really get away with like a 2 gig RAM machine because it's also written in Rust, so it's very memory efficient. You can probably get away with like a 20 megabyte bandwidth, especially if you are co-locating your RPC nodes. But if you're querying RPC nodes over the internet, maybe go for a higher bandwidth. And really, your major cost is your RPC provider subscription. So maybe something like Alchemy or something like QuickNode or I don't know, Anchor, where you can then query all the proofs and everything directly from full nodes that are provided by these services. So it's very, very cheap to run a relayer. And this is kind of how we see interoperability being scaled, because a lot of people are going in the opposite direction, using ZK proofs that are very expensive to generate and of course have very high operating costs. But with Hyperbridge, you can see the costs are ridiculously low, right? And so for the collators, for block producers, it's a bit higher because you have to essentially run a local Polkadot relay chain as part of the collator software. And this, of course, is also pretty huge. I think Polkadot archive is around 3 terabytes. So I think 4 terabyte SSD is good enough. You'd, of course, need a very high bandwidth machine to communicate with the Polkadot relay chain and submit your blocks fast enough. And this should basically work out to around $200 a month. Of course, if you host it locally, with a home staker node, then this cost obviously becomes nothing. And so we just basically look at Polkadot, right? So what does Polkadot's role in Hyperbridge? Well, Hyperbridge is a Polkadot parachain that acts as this co-processor for all this cryptographic proving that needs to happen for cross-chain messaging. But the proofs of this co-processor actually comes from Polkadot, right? And the cryptographic certificate, which I talked about earlier, of the Hyperbridge blocks is produced by the Polkadot validator set. And really, this certificate is just cryptographic signatures, digital signatures coming from the active validator set of the Polkadot network. And really, I think the insight here is that blockchains are just kind of like multi-sigs, right? The validator set is a giant multi-sig. And so then why is this different from our existing multi-sig bridges? Well, let's actually look into that. So on a blockchain, the validator set is actually rotated periodically. In the case of Polkadot, this is every 4 hours. But if you had a multi-sig committee that does bridging, then your signers are never rotated. And the keys sit on the machine, creating opportunities for private key compromise, right? Secondly, the signatures carry what we call on-chain insurance through staking and slashing. So the validators of the Polkadot network, or really the validators of any blockchain, they're staked. They have put up some capital to become validators that can be slashed if they sign incorrectly. But your multi-sigs, your multi-sig committees, they don't have any insurance. They don't have anything to lose. And that's why when these bridges get hacked, it's so very easy to make off with billions of dollars in bridged assets with no consequences for this. Now, the only problem with blockchains as a multi-sig is that the blockchains often have very large validator sets. So, for instance, Polkadot has over 600, and they're going to expand this to over 1,000 validators. But you can actually fix this using aggregatable BLS signatures and through some nice ZK tricks to bring back the cost of verifying these signatures to something that's more permissible. But we can see that in the case of multi-sig committees, they necessarily have to keep their sets very, very small so that it's very cheap to verify, right? And the last thing is for blockchains, joining the set is open and permissionless as long as you have the right stake. You can leave and join the set at any time. But for multi-sig committees, it's necessarily closed and permissioned because of the trust that's required, right? So let's now look at the economics of the Hyperbridge protocol. So the Hyperbridge protocol has fixed operating costs. I discussed the incentives that are given to the relayers. So consensus incentives make up 3 million bridge tokens. Messaging incentives make up around 1.4 million bridge tokens. Collator incentives, of course, make up around 3 million bridge tokens. And of course, we have to pay for Polkadot core time, which is variable, but I think it's pretty cheap. So in total, we see that the cost of running the Hyperbridge protocol is actually around 10 million bridge tokens per year. And well, if we're going to be paying out all of these costs, where's it going to come from? Well, it's going to come from the Hyperbridge treasury, the on-chain treasury, which holds around 40% of the token supply. It's basically the majority holder of the bridge token. And this also gives the Hyperbridge protocol around 40 years of runway. So it literally has 40 years to turn a profit, which I think is good enough. But how does it turn a profit? Whenever users bridge cross-chain messages, whenever users make cross-chain storage queries, the Hyperbridge treasury collects transaction fees. Remember, the messaging relayers are collecting these transaction fees on behalf of the Hyperbridge treasury. And so Hyperbridge needs to process around 10 million messages annually to break even. According to Token Terminal, there's over 1 billion cross-chain transactions yearly. So I think Hyperbridge only needs around 1% of this market share to break even. And at that point, it just continues to make profit. So let's look at some of the Hyperbridge stats so far since we released this. We've saved over 13 trillion gas for all the verification that Hyperbridge has done. We've processed around 50,000 messages. And this is not just from Hyperbridge's, like Polytope Labs' own applications. We also have third-party applications live on mainnet that are actually creating these cross-chain messages and cross-chain transactions. Over 10 million proofs have been verified. This is a combination of consensus proofs, messaging proofs, and we've done over $180 million in transaction volume. Of course, our economic security comes from Polkadot, and that's north of $2 billion. And we now support over 14 major EVM networks, right? And you can see all the networks you support here. All your favorite networks are here. Of course, Polkadot, Hydration, Bifrost, but now Arbitrum, Polygon, Base, Gnosis, Ethereum, Mainnet, Unichain, and we continue to expand support for more networks. So just briefly, quickly into the applications. Polytope Labs, we've developed Token Gateway, which allows you to do cross-chain token bridging using this burn and mint interface. It's also backwards compatible with existing ERC20 deployments through a lock and mint interface. And you can bridge any token and also execute arbitrary call data. And this already powers the DOT token, which is live on mainnet today, VDOT, ZK Verify, Manta, and on some other tokens as well. And very recently, we launched Intent Gateway, which allows you to do fast cross-chain transactions. These are verifiable cross-chain intents, and they will happen under 30 seconds for most transactions. But the real innovation here is if your transactions are not fulfilled, if your cross-chain orders are not fulfilled, then you can permissionlessly ask for a refund on the Hyperbridge app, and you'll get your refund immediately, right? Because all of this is powered by proofs, and Hyperbridge can actually look at the state of the counterparty chain and see that your orders are not fulfilled, right? But of course, there are third-party developers building on Hyperbridge, and we're working with Hydration to deploy their version of intents. They're also working on a price oracle for some staked versions of ETH. Bifrost is doing a price oracle for their liquid staked tokens. They're also going to be launching this asynchronous V token minting. And there's been a few hackathons that have successfully deployed applications on Hyperbridge on testnet. We're also thinking about potentially new ideas for applications. We see a lot of opportunities in verifiable price oracles, also in cross-chain governance, where you can do governance on one chain, but read the results of that governance from any chain. There's also lovely things around cross-chain identity, where identity is on one chain, but you can read that identity from multiple chains. Also, we see opportunities for historical storage queries that allow contracts to look at the historical state of the blockchain they're on. And this could be useful for incentive distribution protocols like Merkle. We've recently released our developer SDKs. The Hyperbridge core contains all of the Solidity interfaces for Solidity applications. We have Hyperbridge SDK for wallets and front ends. It's basically a TypeScript SDK. And then we have the subquery indexer as well as the filler for our intents. So our roadmap, I'm really happy to announce here for the first time on the Subzero stage that Hyperbridge will be natively available on the Polkadot Hub. And so this means that applications on the Polkadot Hub can use Hyperbridge to interact with blockchains outside of the Polkadot ecosystem, making cross-chain storages, queries, and also cross-chain messaging. We're also working on BLS Beefy. We're working very closely with the Parity team to bring BLS Beefy to life, which will finally decentralize Hyperbridge. Because right now, the Polytope Labs team, we run the consensus prover for Polkadot consensus. And so we would like to make this decentralized using a BLS aggregatable signatures. And we also have upcoming EVM integrations, I would say majorly Arc, Tempo, Monad, Sonic, Tron as well, because now they're working on state commitments and bringing state commitment support to Tron. And of course, we now have Cosmos support, so we can support the Cosmos EVM chains like Say, Chronos, and Injective. And that's my talk. Thank you for watching.